Dear students, this is part of NMR statistical analysis. We have so far discussed about the basics of NMR. That means what is NMR spectroscopy, what is its theory, or what is the theory behind the NMR spectrum and all. We were discussing about the shielding and de-shielding in the class. Now we are going to discuss in detail what is shielding and what is de-shielding. Okay, so we have certain information obtained from the NMR signals. When we are considering the NMR signals, first of all, the number of signals in an NMR spectrum will show how many different types of protons are present in the given compound. Second is the location or position of the signals, and this will show how shielded or de-shielded the proton is. Third one is the intensity or height of the signals will show how many number of protons of that type are present. And fourth one is the signal splitting show how many adjacent protons are present in the given organic compound or in a given functional group. So the information obtained from NMR signals are, first of all, the number of signals will show how many different types of protons are there. For example, if you are considering a compound CH3CH2OH, it is actually containing 3 different types of protons, so it will give 3 types of signals, or the number of signals will be 3. And second is the location or position of the signal. The CH3, CH2 and OH will be appearing in different positions, and the intensity, that means the height of the field, will show how many number of protons of a particular type is present in the compound. And the splitting will be discussed in detail. Just know that the signal splitting, that means a single signal can be appeared as a multiplex, and that means it will be having a number of signals combined together, and the splitting will show about or give the information regarding the adjacent protons or the environment. Okay, now we have just had an introduction regarding the shielding and de-shielding. So when we are considering a nucleus, it is spinning, and in the NMR technique, we are applying an external magnetic field, and in the absence of an external field, the proton is said to be isolated and it can freely rotate in any direction. But when we are applying an external magnetic field, it can feel the external magnetic field. Okay. And if it is an isolated proton, it will feel only the external magnetic field. But look at the second picture. When the proton is surrounded by an electron density, then when we are applying an external field, this proton and also the electron field will feel the external magnetic field. That means, in addition to the external field, the proton will feel the field of electron also. So that is where we are going to explain the shielding. So in this case, that means when the proton is feeling the external field as well as the field created by the electron, we can say that the proton is said to be shielded, or the nucleus is said to be shielded. Now, this is given in sentences. That means if all the protons absorb the same amount of energy in a given magnetic field, no such information could be obtained. But when protons are surrounded by electrons that shield them from the external field, then the circulating electrons create an induced magnetic field that can oppose or support the external magnetic field. The case is shielded protons. That means next we are going to explain the case of shielding. The magnetic field strength must be increased for a shielded proton to flip at the same frequency. That means when we are considering this image, this is an isolated proton or a naked proton, and the absorbency is around 14,092. That much amount of Gauss's, that means the unit of magnetic field, Gauss's it will absorb when we are giving an external magnetic field of 60 megahertz. Okay. Now, when we are having a particular amount of external electric field, that means the electrons are shielding the nucleus, then when shielding is produced, what happens is this field, that is the field created by the electrons, will oppose the applied field. So in order to overcome this fielding effect, we must apply a higher external field. That means, in the case of NMR, this proton has to be in the effect of this external field. That means, the NMR signal is produced when the proton or the nucleus is interacting with the external field. Okay. So, in between the proton and external field, if there is another field that is created by the electrons, and when it is said to be fielding, then this external field should oppose the applied field. Okay. In the case of de-shielding, this field is supporting the external field. So, the proton will feel a higher field in the case of de-shielding, and in the case of shielding, the proton will feel a lower field. Okay. But in order to obtain the NMR spectra, the external field should be felt by the proton. In order to do so, we have to apply a higher field in the case of shielded protons. Next is, when we are considering a particular molecule, there can be shielded and de-shielded protons in the same molecule. Okay. Now, depending on their chemical environment, protons in a molecule are shielded by different amounts. When we are considering this functional group or this organic compound, that is CH3OH methanol, the CH3, that is HHS, is attached to the same carbon atom, and these three protons are said to be more shielded, and their association will take place at a very higher field. When considering this OH, oxygen is an electronegative atom, so it will attract the electron density towards the oxygen atom, and so there will be a reduction in the electron density. Okay, so when electron density is lesser, it is said to be de-shielded. Okay, or less shielded. So in the case of less shielded proton, that means the electron density around hydrogen is absorbed or attracted towards the oxygen. Now electron density is around this oxygen, so this proton is free to shield the external field. That means this hydrogen atom, which is attached to an electronegative atom, is said to be de-shielded, and it requires only a very less amount of external field in order to get the NMR signal or in order to resonate. Now, this is a typical case. That means when we are considering the acetylene protons, this is a simple example in order to explain the shielding and de-shielding. So, acetylene is a triple bond compound. That means C triple bond C is the structure. The triple bond is represented by the cylinder. Okay. So now it is having a nucleus. So obviously it will create a magnetic field, and this magnetic field is actually rotating around this bond. Okay. And this rotation is like this. So it is just similar to the magnetic field we have created during the plus 2 classes, that is during the experiment of creating the magnetic lines of force. So they are rotating around this, that means it will be in this direction. Now we are applying an external field of strength B0. Then around this molecule there will be an induced magnetic field, and now when you are looking at this position, both these magnetic lines are pointing upwards. That means these are in the same direction. That means the induced magnetic field is aligned in the direction of the external magnetic field. So the field felt by the nucleus of acetylene will be the sum of these two. Okay, at one point. Now consider the point which is close to the carbon atom, or which is approaching the triple bond. Now you can see that the direction of the magnetic lines of force is reversed. This is in the upward direction. Now this magnetic lines are in the downward direction. So the induced field is opposing the external field. Now this is said to be shielded. This is the de-shielding condition. where the applied field and the induced field are on the same direction, and this is the opposing condition or shielding condition where the applied field is against the induced field or reverse. Where the induced field is opposing the applied field. So this is a simple example in order to explain the shielding and de-shielding. That means when the magnetic lines of force are coming closer to the bone, it is shielding, and when it is far from this bone, it is de-shielding. So in the same molecule, we can have shielding and de-shielding effect. Now this is benzene or aromatic protons. So in the case of aromatic protons, the lines are rotating in this direction. Okay, that means it is rotating like this. So this is the electron ring current. Now this protons, that means the hydrogen atoms which are on the 2 ends, that is the para positions, are actually de-shielding the protons, or these protons are de-shielded, whereas this protons which are on the meta and also on the ortho positions are said to be shielded. Okay, so here it is supporting the para protons, whereas it is opposed by the ortho and meta protons. So this protons are, the induced field is reinforcing, and we are saying that this is de-shielding, but here it is opposing, so we can say that this is shielding. So in the same molecule, we can have shielded protons and also de-shielded protons. So depending on the shielding and de-shielding, we are having a particular parameter called the chemical shift, and it is measured in parts per million. It is represented by the letter delta, and delta can be represented by the equation mu x, or frequency of the sample minus frequency of the reference in hertz divided by operational frequency in megahertz. Okay, so the ratio of shift downfield from the CMS. CMS is the reference compound, and now what is the specialities of this CMS? So this is CMS or tetramethylsilane. Actually it is slightly clubbed. It is CH3 4 times. So TMS is added to the sample, and since silicon is less electronegative than carbon, the TMS protons are said to be highly shielded. That is, there is no group which is concentrating or which is attracting the electron density from the methyl group. That means all the electron density is surrounding the methyl group. So when we are having 4 such methyl groups, it is said to be highly shielded. So there is no organic compound which is that much shielded when compared to the tetramethylsilane. Okay, so all the organic protons will absorb downfield or towards left of the EMS signal. So we can represent EMS in the scale or in the NMR signal scale in a value 0. Okay, that is EMS is having a 0 value. Now the factors affecting chemical shift are electronegativity, cumulative effect of electronegative substituents, distance from the electronegative atom, and also the de-shielding effect. This is the delta scale, or how we are representing the NMR spectrum. Okay, that means NMR spectrum is represented in terms of the chemical shift. This is the operational frequency, or the frequency where the protons are resonating, and CMS is resonating at a very lower field. That means it does not require an external field, or reverse it is highly shielded protons, and the shift, or it is selected as a reference compound, so there is no shift or change in the field. It is represented in the position 0. Okay, this is an information obtained from the delta scale or the chemical shift scale. Now all the shielded protons will be closer to the 0 value, and we require a higher field in order to resonate. So we can say that shielded protons are resonating at a higher field, and the de-shielded protons are resonating at a down field or a lower field. So this is a typical example to explain the